All right, so maybe we should get ready to get started. So hi everyone, welcome to the last day of the Lattice workshop and a natural transition to the quantum workshop that's going to take place next week. Today we're actually going to talk about applications of Lattice cryptographic techniques in the quantum regime. And the first talk of the morning or whatever other hour you're at is by Urmila Mahadev, who is going to tell us about a quantum version for fully homomorphic encryption. Please, Urmila. Oh, let me just remind the protocol for asking questions. So if you're a panelist, then you can just unmute yourself and ask a question politely, please. And as attendees, you have access to the Q&A sidebar, and you can type your questions there. And either Urmila is going to see the questions herself, or I'll try to keep an eye out. Me and the other panelists will try to keep an eye out and either address the question or refer to Urmila. All right, Urmila, please.
Thanks, Vika. So like Vika said, my talk is on classical homomorphic encryption for quantum circuits. This is in both quantum computing and cryptography. And I try to keep the quantum computing parts pretty easy to follow, hopefully, but I encourage a lot of questions as I don't have that much content, and I did that to create room for questions. So you should feel free to ask questions during the talk and after. So I'll get started. And to start, I'll start with a topic that should be familiar to most of you in this audience, which is classical homomorphic encryption. So in classical homomorphic encryption, you have a weak client and a much more powerful server. And the goal of the client is to privately delegate a computation to the more powerful server. So he wants to encrypt some input data M, and then the server should be able to compute a classical circuit on top of the encrypted data. So the server never learns anything about the data while he's computing. Sorry. Yeah, so the server never learns anything about the data while he's computing. And this was first shown to be possible by Craig Gentry in 2008. And in my talk, the setting is going to be similar, but now the server will be a quantum machine. And when I say a weak client, the client is a classical machine. So that's why the client is much weaker than the server in this setting. And now the question is the same. Can this weak classical client use the computing power of a quantum device while maintaining privacy? So ideally, what this classical client should be able to do is send over some classically encrypted data to the server. And then the server should be able to compute a unitary on top of the data. So instead of applying a classical circuit homomorphically, now he wants to apply a general quantum circuit, which we represent as a unitary quantum operator. Zvika, I don't know if there are questions.
So far, you're okay. I'll let you know.
Okay. Yeah, so the goal of the server is now to compute a unitary transformation on top of the classically encrypted data. And the first question here is whether we can just immediately use classical homomorphic encryption schemes for this purpose. So can the client just classically encrypt his data, send it over to the server, and then can the server apply a quantum circuit on top of classically encrypted data? And it turns out that there is a property of classical homomorphic encryption schemes which makes this quite difficult. And that property is that classical homomorphic encryption schemes are inherently probabilistic. There are many different encryptions of a single bit. And that's necessary because in classical homomorphic encryption schemes, the server is computing on top of encrypted data. So if the encryptions were deterministic, let's say there was a single encryption for a bit 0, then the server could always figure out what's going on by maybe applying different computations and seeing where the different computations end up. He could compare the output ciphertext. So this is an inherent property of classical homomorphic encryption schemes, but it seems to conflict with the quantum property of interference. So now let me tell you what this quantum property is. And to tell you what the quantum property of interference is, I first need to tell you what the Hadamard transform is. This is a key operator in quantum computation. And all the Hadamard transform is, it's the quantum Fourier transform. So it's a reflection about pi by 8. And this picture shows you the reflection, and on the bottom, you can see what it does to quantum states. So it maps a 0 qubit to uniform superposition over 0 and 1, and it maps a 1 qubit to a uniform superposition over 0 and 1 as well, but now there's a phase of -1. Now that I've introduced the Hadamard transform, I can tell you what interference means. So interference says that elements of a superposition representing the same bit string, but with opposite amplitudes, must cancel. And you can see this with the Hadamard transform. So if I take the Hadamard transform and apply it to a uniform superposition over 0 and 1, I should get 0. Another way of seeing this is we can break this down. It's a linear operator. And if you apply it to 0 first, you get 0 plus 1. And if you apply it to 1, you get 0 minus 1. And what happens is that the two ones are canceling out. So that's what I mean by interference. These two elements of the superposition, which are representing the same bit string, but with opposite amplitudes, must cancel. Now, if we try to use homomorphic encryption in the most naive way, let's say what we do is we just replace these bits with classically encrypted bits. So replace 0 with the encryption of 0, replace 1 with the encryption of 1. Now, this is exactly where the issue of having many different encryptions for a single bit really messes up whatever quantum computation we're trying to do. Because now, let's say the two encryptions of 1 were different. They might not cancel. There's no reason that I should think they cancel. So now if I just look at this naively, I should not get encryption of 0 out, which is what I need. And this is why the probabilistic nature of homomorphic encryption seems to come in conflict with properties that we need in quantum computing. And so far, what I've done is I've just told you.
So Urmila?
Yeah.
This is Vinod.
Hi, Vinod.
If you instead think of the encryption of 1 as being not an encryption of 1, but the superposition over all encryptions of 1, then this would cancel.
Well, what do you mean all encryptions of 1? Because noises are changing, right? Like what if you have a superposition and then the noise distribution changes as you apply operations? So you'd have to say that superposition remains constant throughout the computation.
I see. This is specific to LWE, but if you think generically of sort of, of encryption schemes, I'm saying, superposition over all randomness, like pick all possible encryptions of 1.
Yeah.
Which is actually not well defined for LWE. I see what you're saying,
yeah.
But if you could, then this particular problem would not exist. Okay.
You're right. That particular problem
but don't we need?
But I'm not quite sure what would happen with homomorphic computation.
Okay, got it.
You're right.
I have a follow-up question. So if we were to do this superposition, then the scheme is no longer encrypted classically. I mean, we're no longer encrypting classically, right? I thought that here we really wanted to do classical encryption, but
no,
compute.
I think Vinod is just suggesting. So here I suggested one way of using classical encryption for quantum computations, and Vinod is suggesting a different way of using classical homomorphic encryption for quantum computations.
Okay. So how would you prepare that superposition that you would need here?
That would be tricky, Vinod.
That's a problem. But I don't want to sort of back.
Okay, sure.
Line of thought.
Sure. Yeah, I just thought I missed something. Okay, thanks.
Yeah. Okay. So like Vinod just said, this is just one way of using classical homomorphic encryption schemes for quantum computing. And there are many other ways. So this way seems to run into an inherent obstacle, but there is one other way which seems much more natural in the quantum setting. And I'm going to focus on that method in this talk, and it's called the quantum one-time pad. So the quantum one-time pad is just the classical analog of the one-time pad. And I'll first tell you what this encryption looks like. It's an information theoretic encryption. Then I'll convert it to the computational setting and show how it can be used in the setting of quantum homomorphic encryption. And again, this one-time pad encryption is just, it uses classical homomorphic encryption in a different way to encrypt quantum states. So here's the information theoretic method of encryption. Question? No? Okay, here's the information theoretic method of encryption. We're starting with a single qubit state psi, and we like to encrypt it. And it goes in steps. The first step is to sample a bit z at random and apply the Pauli phase operator to the state. So what this operator does is if z equals 1, it inserts a phase of -1. And if z equals 0, it doesn't do anything to the state. The next step is called the Pauli bit flip operator, and it's the same as a classical one-time pad. So here a bit x is sampled at random, and now the qubits are flipped in superposition based on the bit x. So if x is equal to 1, each bit is flipped, and if x is equal to 0, nothing happens. Now when you combine x and z, this is called the Pauli one-time pad, and it information theoretically hides the single qubit state. So if you choose x and z at random, apply the Pauli operators to the state, all information about the state is gone. This is an information theoretic one-time pad, but just like in the classical world, you can take an information theoretic one-time pad and convert it into a computational encryption by including the classically encrypted one-time pad keys. So this is exactly what's done here. Now we have a two-part encryption. The first part is the one-time padded quantum state, and the second part is the classically encrypted one-time pad keys. Now this is a computational encryption of a quantum state, which uses classical homomorphic encryption, because to encrypt these keys, I will use a classical homomorphic encryption scheme.
Hi, Urmila.
Yeah.
This is Rachel. Yeah, I just want to ask a question.
Uh-huh.
Maybe also helps other quantum dummies in the meeting. When you say that the information theoretically hide the state, I presume what you want to hide is alpha 0, alpha 1. Can you explain a little bit more in which sense it hides alpha 0, alpha 1?
Sure. Okay, so let's first go to a very simple case where this state is essentially classical. So let's say alpha 0 equals 1 and alpha 1 equals 0. So this is just the 0 qubit. Now you can see that just this second step, information theoretically hides the state because it's either 0 or 1 with equal probability. So that's the first step. And now the second step, that was just for classical states. And what that first step does is a phase operator. It kind of hides the properties of the superposition. So now imagine that you had a 0 plus 1 state. What the phase operator does is it either maps it to 0 plus 1 or 0 minus 1. But these are orthogonal states. So now he has no idea which of these two states he's in. And so that completely hides the phase information, which is essentially the information about the superposition.
I see. Okay, thank you.
Yeah, no problem.
I actually think that this is maybe a good point for other questions. If other people or the panelists or attendees have additional questions, because we, I guess, stepped into the technical quantum regime, and I'm assuming that people might want to ask.
Yeah.
So just a clarification question. This is Shafi. So you still have the information theoretic encryption. In addition, you're encrypting the choices that were made, the random choices that were made here. So at this point, there's no benefit in this thing, right? You've added information,
right,
that is unnecessary for. Okay, good.
Yes.
What would have been in the above thing? The one-time pad is Z and X. So you're essentially encrypting the pad. Is that right?
Yes.
Good. I mean okay.
It's not useful right now, but it'll be useful for the homomorphic part, which I'll get into in the next slide.
So
Yeah,
I just wanted to say, so you're encrypting using a key, and then you're also sending along an encryption of the key.
Yes.
Okay.
Okay, so I'll continue to the next slide. So far what I've done is I've just told you how to computationally encrypt the state. And now I need to link this to homomorphic encryption and say how the server can apply operations on the state. So what's happening right now is that the classical client just has some data, and he first encrypts it and sends it over to the quantum server. So in this picture, it might be a little confusing because I keep saying classical client, but in this picture, it looks like the classical client is sending over classical keys as well as a quantum one-time padded state. And the thing to observe here is that actually, if this state psi is a classical string, then the one-time padded quantum state is just the one-time padded classical string. So this thing that looks like a quantum state is actually just a classical string. So in the case that the input data is classical, the one-time padded quantum state is also classical. So the client can be entirely classical in that case. But for full generality, I'm just going to cover the case where the client wants to send over an arbitrary one-time padded quantum state, and the server should be able to apply a general quantum operation on this state. So how does that look? How does the server apply a general quantum operation to this one-time padded state? It turns out that for most quantum gates, what the server can do is split his computation into a classical computation on the one-time pad keys and a parallel quantum computation on the one-time padded state. So this is what happens for most of the quantum gates. The quantum server applies a quantum operation to the one-time padded state. Because of this quantum operation, the one-time pad keys will change. To account for this change, the server applies a classical homomorphic encryption to the one-time padded keys to update his keys according to which gate he applied. So far it's pretty straightforward, but there is one complication. There is one gate which is required for a universal set of quantum gates, for which the server can't just split the computation into these parallel classical and quantum computations. For this gate, what the server has to do is take one of his classically encrypted keys and convert it into a quantum operation. So he has to take a classically encrypted bit, and based on that bit, he has to conditionally apply a quantum operation to his one-time padded state. And this is the key difficulty in quantum homomorphic encryption schemes. How do you take a classically encrypted bit and convert it into a quantum operation? And
so
this is
Urmila, at some point you're going to tell us a bit more about the quantum computation model, about gates and universal gates and so on.
No.
No, we don't need to know.
You don't need to know. There's going to be one gate that you need to know about called the C0 gate, and I'll get into that on the next slide. But all I'm going to say about quantum homomorphic computation is that it boils down into these parallel classical and quantum computations. And the hard part is connecting the two, doing a quantum gate controlled on a classically encrypted bit. Okay, so at this point, this is a good time to tell you a little bit about previous work. So far, the setup that I've told you with the one-time pad keys, converting them into computational encryptions, and then running the computation in parallel, this was all known in previous work. And in all of the previous work, they knew that the key difficulty was this conversion of a classical ciphertext into a quantum operation. And to take care of that difficulty, they required quantum states. So the client had to send over quantum states to the server, and this quantum state had some secret information encoded into it, which allowed the server to do this conversion, to take one of his classical ciphertexts and apply a quantum operation based on it. Now, these schemes were very interesting, and they led to a lot of advances in the field of delegated quantum computing, but there was a key difficulty, and the difficulty is as follows. If the client is sending over quantum states to assist the server in the computation, these quantum states cannot be reused. So each time the client wants to delegate a quantum computation, he has to send over this set of quantum states. Moreover, the number of quantum states corresponded to the size of the quantum circuit being delegated. So if you put that together, what it's saying is that with these schemes with the quantum client had to run a quantum computation of the same size as the quantum server. So this was the key obstacle, and that's why using a classical client is very different, because you don't have these issues with the quantum state. All the server has to do is use his classical information to do this conversion from a classical ciphertext to a quantum operation. Now, the next thing, like I said to Zvika, I'm not going to talk any more about the first bullet point. The rest of this talk will focus on the second bullet point, how to convert a classical ciphertext into a quantum operation. So now is a good time to ask questions if you want to clarify the bigger picture before I get more into that second bullet point.
Yes, let's take a second for everybody to sort of see if they're up to speed or want to ask the question. Right, looks like they want you to go on.
Okay.
So not
yes.
Delayed question. So just to understand what you are sort of looking for here. You know, if you have a qubit alpha 0 plus beta 1, right? You want alpha 0, so this is sort of following up on what Peter said on the comments, alpha 0 plus beta times unitary applied to 1, something like that. That's what you want. If the bit is 0, you do nothing. If the bit is 1, you apply unitary. And if you have a superposition, you want to do this.
Yes.
So now you only have an encrypted bit.
Yes.
And you can't possibly do this because that would reveal information about, that would violate semantic security. So instead, what you're hoping to get is an encryption of that qubit under,
exactly.
Under the key. Okay, sounds good.
Yeah.
Thanks.
And if anyone didn't follow, I'm going to cover exactly what Vinod just said in the next slide. Yeah. Okay, so now let me go into this conversion from a classical ciphertext into a quantum operation. And the first thing I need to do is tell you what that quantum operation is, and then what it looks like to convert a classical ciphertext into that quantum operation. So this quantum operation is called the C0 gate. And all the C0 gate is, it's a quantum version of the XOR gate. So it's a reversible XOR gate. And that's what this picture depicts. So you have two wires, they're bits A and B. The first wire remains unchanged. And in the second wire, we're XORing the first bit into the second. And in this picture, it looks like you just have bits, but in general, these bits will be in superposition. Now, what the quantum server has to do during the homomorphic computation is he has to apply a C0 conditioned on an encrypted bit. So he'll get as input some encrypted bit S, and he should either apply the C0 or not based on S. If S is equal to 0, do nothing. If S is equal to 1, apply the C0 gate. And here's what this looks like in terms of a circuit diagram. So now there's one more wire, which is the classical encryption of a bit S. And now if you look at that third wire, what's happening is that A is XORed into that register only if S is equal to 1. And if S is equal to 0, nothing happens. And in this third line, I just wanted to write the state in superposition and show you what the output should be in superposition. So in general, the server should be able to take as input an arbitrary 2-qubit quantum state, a classically encrypted bit S, and output the result of conditionally applying the C0 gate to his input quantum state. So this operation is quite strange because what the server is doing is he has this classically encrypted bit S, which he can't understand, so it's hidden from him, but somehow he is applying a quantum operation based on a bit that he cannot see. So that's why this is really the crux of quantum homomorphic encryption, because it's quite difficult to take a hidden classical bit and convert it into a quantum operation. And like Vinod said, as I've written it here, this is impossible, because if the server can do this conversion, if he can just compute this quantum state for an arbitrary 2-qubit quantum state, he can set, let's say, A equals to 1, B equals to 0, and he can learn the bit S. So the detail that I skipped over was that this output state, so when the server is applying this operation, the output of applying the conditional C0 has to be encrypted. And it's going to be encrypted with the one-time pad that I just showed you. So this entire operation of converting a classical ciphertext to a quantum operation, to the quantum C0 operation, is called the encrypted C0 operation. And now that I've told you what this operation is, let me just summarize what I've told you about quantum homomorphic encryption so far. So I told you that the encryption scheme that I'll be using is the computational version of the Pauli one-time pad, which consists of sending over classically encrypted keys, as well as a one-time padded quantum state. Then I told you that the homomorphic computation mostly boils down to parallel classical and quantum computations, where the server is applying quantum operations to his state, and then updating the one-time pad keys classically as he goes along using a classical homomorphic computation. However, there was one key difficulty, which is when the server has to apply a quantum operation, which is dependent on the classically encrypted keys. And I called this operation the encrypted C0 operation. And here's what it looks like. The server takes as input the encryption of a bit S, an arbitrary 2-qubit quantum state, and he applies the C0 conditionally to the 2-qubit quantum state, and he outputs the encrypted value of the output. So this encryption matches this first picture where he's outputting classically encrypted keys and a quantum one-time padded state. And so this was the suitable encryption that I referred to earlier. The state is not in the clear, it's encrypted by the computational Pauli one-time pad. Now I'm going to continue to building the encrypted C0 operation. And once I build the encrypted C0 operation, then I will eventually link back to classical homomorphic encryption schemes. So what I'll say is that certain classical homomorphic encryption schemes allow this conversion from a classically encrypted ciphertext into a quantum operation. And therefore, those schemes can be used to homomorphically evaluate quantum circuits. So that's the final result. The final result is that there are classical homomorphic encryption schemes which satisfy certain requirements which enable them to be used for homomorphic evaluation of quantum circuits. And that's what I'll go into next, into building the encrypted C0 operation. And before I continue, are there any questions so far?
Another question. If you look at the distribution of X and Z that come out of this operation, right? Will it be uniformly random pair of bits?
Yes.
Great, like information theoretically uniform. Right?
Yes. Okay, got it. Well, yes, if the server is honest, that's what you mean.
Right, sure,
okay.
Sure.
Yeah.
There's also a question from Evgeny. Do you want to turn on your microphone? Do you have permission?
Sure. I mean, it's not critical. I was just curious. Quantum transformation should be reversible. So from your picture, it looks like S kind of is only participated in C0, but the information about S could be lost. And somehow, it's not. I thought that all this quantum transformation should be reversible, and it appears that S is lost.
Well, first of all, so S can't be lost because it's classically encrypted data.
So this doesn't disappear. No, but you convert it, right? You start with encryption of S. Now you have encryption of XZ. X and Z are independent of S. So on the right-hand side, the only dependence on S is C0 S. And it wasn't clear for me that this information theoretically determines S.
It does information theoretically determine S.
That's okay.
If you have the encryption of XZ, you can decrypt them and then decrypt the state and then find C0 S. But I don't think I'm getting your question because information about...
I just thought that don't you get A plus BS and A plus BS, let's say if B0, for example, information about S is lost?
But encryption of S is classical, so I could copy it on the side and then I.
Okay, so this means it's just like incomplete picture. So this thing doesn't disappear. Okay, I just wanted to make sure.
Yeah.
Yeah.
Okay.
Any more questions before I continue? Okay, so now I'm going to get into the encrypted C0 operation and how to build it. And in order to tell you how to build the encrypted C0 operation, I need to tell you about a primitive called Trapdoor claw-free functions because these will be the main building block for the encrypted C0 operation. So let me start by defining Trapdoor claw-free functions. These were introduced by Goldwasser, Macaulay, and Rivest in 1984. And a Trapdoor claw-free function pair is a pair of functions F0 and F1, which are injective and they have the same image. And then the hardness property is that it is computationally difficult for either a quantum or a classical machine to find a claw, which is a pair of pre-images which map to the same point. And then the trapdoor property says that if there is a trapdoor, so if an algorithm has access to a trapdoor, then there is an efficient algorithm for inversion. So given the trapdoor and an image Y, this algorithm can output the two pre-images of Y. Now, if you put those two conditions together, what I'm saying is without the trapdoor, both quantum and classical machines cannot find even a single pair of pre-images which map to the same point. That's the claw-free property. But with a trapdoor, it's very easy to take an image Y and invert it to find the two pre-images which could have mapped to that image Y. Now, these trapdoor claw-free functions are pretty interesting in the quantum setting because quantum machines have a unique capability. What a quantum machine can do is sample a random image Y and create a uniform superposition over the corresponding claw, so over the two pre-images corresponding to Y. I'll tell you in a second how exactly the quantum machine does this, but for now, I just wanted to talk a little bit more about this superposition. So the superposition is interesting because it seems like it contains information about both pre-images, But I just said that even for a quantum machine, it's hard to find both pre-images. It's hard to find x0 and x1. So how can it be that it's hard to find the pre-images, but it's easy to create a superposition over the pre-images? And the main thing to note here is that just creating a superposition over the pre-images is not the same as finding it. In order to extract any information from the superposition, the quantum machine has to measure the superposition. So he can measure it in many ways. One thing he could do is measure it in something called the standard basis. And in that case, the superposition would just collapse to either 0x0 or 1x1 at random. And in that case, all the quantum machine has done is sample a random pre-image image pair. And that's not hard. That's classically reproducible. It doesn't take advantage of the fact that the quantum machine could create this interesting state. But if the quantum machine measures it in the Hadamard basis, which is the quantum Fourier transform that I introduced earlier, then he can obtain some information which is correlated to both x0 and x1. And this is the kind of thing that we believe is hard to do classically. And in a joint paper with Zvika, Paul Cristiano, Meshwaz Rani, and Tomas Vidic, we introduced this advantage and we showed that using this superposition, the quantum machine can produce something that a classical machine cannot reproduce. And then we use this advantage for various things. So we used it to classically test quantum machines. We used it for certified randomness generation, and we used it to classically verify quantum computation. And in this talk, I'm not going to go into any of that because all I need here for homomorphic encryption is I need the fact that the quantum machine can create this uniform superposition over a random quad. So I'm not going to say anything more about the previous work, but now I'm just going to tell you how the quantum machine creates this uniform superposition over the clock. And here's how he does it. So this is his goal. And what he does is he first creates a uniform superposition over the domain of the function. So you have a single bit and then you have a longer binary string x. Then the quantum machine applies the classical function in superposition. So he chooses to either apply f0 or f1, depending on that first bit b. Finally, what the quantum machine does is he measures the last register to obtain an image y. And now the way a superposition works is if you measure that last register, then the remaining registers will collapse to only those values which are consistent with y. So if it was an injective function, for example, then when you measure that last register y, the pre-image register would just collapse to one value. But now, since we know that there are two pre-images for every image, one from f0 and f1, what happens is that when you measure the last register to obtain an image y, that pre-image register collapses to a uniform superposition over the only values which are consistent with y, which are x0 and x1. And this is just due to the entanglement in the state and how quantum superpositions work.
Question?
Yeah.
So this might be a silly question, but step 1, is it efficient?
Yes, and the way it's done is the Fourier transform. If you just take the Fourier transform and apply it to 0, it maps to 0 plus 1. And if you apply it to a longer string, like 0, like n 0 bits, then you get yeah.
Sorry, I thought that the domain of, you're applying this superposition over the domain of x, I thought. And isn't the domain of x exponential?
Yes, but if the domain size is exponential, but you can think of the domain as all bit strings of length n. And so all I'm asking is...
Oh, yeah, right.
Yeah.
Okay, sorry, thanks.
Yeah, no problem. Okay, any more questions about trapdoor claw-free functions in quantum computing? I'm really going to be relying on this fact that the quantum machine can create a uniform superposition over the claw, so it's a good thing to understand at this point. Okay, so
I guess I have one question. So you're saying that you're going to collapse to two pre-images. What happens to their pre-images? So if I sort of keep going backwards, is there any, do you see what I'm saying?
No.
So suppose that you had an iterated squaring here. If we take a particular implementation of claw-free permutations. So I'm thinking about y as a quadratic residue, say, and then I'm taking square roots and then I want to think about taking square roots of those square roots in case they are themselves square. Is there any retaining in any kind of sense? I mean, for me, this is all a little bit of voodoo, but of the, let's say, the fourth root?
I don't quite understand your question because so this initial superposition in line 1, that's where I'm picking the domain. So if you want to have this nested kind of thing, then wouldn't you have to have a different domain here? Because I'm choosing the domain of one function.
Right, but if we're in a world where this what you're picking in the domain itself actually is a codomain of another function. I know that you're picking in the domain, but this domain itself represents something that you could invert on. I mean, maybe Vinod can interpret my question.
Yeah.
So I'm not sure. So you could, if you think of FB as a simpler function, kind of iterated many times, and B is not a bit anymore; it's a sequence of bits, and
Right.
Each iteration where you either pick one of the the first simple function or the second simple function. You could imagine that, right? And then you can create a superposition over all the exponentially many paths. You could do the same thing, really.
Okay, so to begin with, okay.
That makes sense. And then when you just measure it the first time, you'll still have many pre-images left, and then you keep collapsing it. Is that what you're saying?
I'm saying that these trapdoor permutations were used. This one claw, actually, there's a lot of strength in it in making a function where rather than F0 and F1, you're thinking of F substring, and then there might be some strength in being able to do this. But
I guess conceptually, one way of looking at it is instead of having two functions with the same image, you could have exponentially many functions with the same image that you can build from the two functions, sort of just generically, as long as you can iterate these guys. And then, I mean, so I guess the question could be, is that sort of thing useful at all beyond what you're doing?
So that's an open question.
Yeah, we tried to use it in various ways. We haven't, I don't know what it's useful for yet, but maybe.
Yeah.
Okay.
Okay. So.
Any other questions?
Yeah.
There was some discussion on the chat. Anybody wants to bring up the question? No, looks like everybody's satisfied. All right.
Okay, so now that I told you about trapdoor claw-free functions, I need to link them back to homomorphic encryption. And it turns out that trapdoor claw-free functions are very useful in building this encrypted C0 operation. And to tell you about that, I'm going to start by defining a specialized type of encryption, where the encryption is just a trapdoor claw-free function pair. So now I'm going to tell you how to encrypt a bit using a trapdoor claw-free function pair. And the purpose of telling you about this encryption is because what I'll tell you is that with this specialized encryption, so if this encryption of the bit S is just a trapdoor claw-free function pair, then this encrypted C0 operation is very easy. All the server has to do is use the trapdoor claw-free function pair to create a uniform superposition over a claw, and he's essentially done. And then in the final step, so I'll tell you that it's easy with a TCF encryption. And in the final step, I have to link back to classical homomorphic encryption schemes and show how we can use similar techniques to do this conversion with a classical homomorphic encryption scheme. So to start, what does it mean to encrypt a bit using a trapdoor claw-free function pair? Now, to do this, I'll define a slightly different TCF pair. It's almost the same, but there's a bit of different notation. So the first thing I've done is I've split up the domain. Now you have a single bit, and then you have the rest of the domain, which is some set R. Think of it as bit strings again, and then you have the same image Y. And now the first conditions are the same. It's injective. The two functions have the same image. There's a trapdoor, and I've written the clause differently. Now mu0 and mu1 are bits. They come from the first part of the domain. R0 and R1 are longer strings, and the claw-free property should still hold. And the final condition here, which is what makes it an encryption, is that there is an extra property. For all claws, the first bit of the claw hides the bit S. So mu0 XOR mu1 is equal to S. And this is why I'm referring to it as an encryption, because now in each claw of this TCF pair, we are hiding the bit S. So this is just a different form of hiding the bit S. And now I'm going to show you how this TCF encryption can be used for the encrypted C0 operation. So remember the goal of the encrypted C0 operation. The server is given the encryption of S. Now in this case, the encryption of S is just this TCF pair, F0 and F1. Given this encryption of S, the server wants to conditionally apply the C0 operation to an arbitrary 2-qubit quantum state. So this is our arbitrary state, and he's applying the C0 to the power S, which means if S equals 0, he's doing nothing. If S equals 1, he's XORing A into the second register. And just for simplicity, I'm going to assume that B equals 0. And so all we're doing is we're computing A.S in the second register. Now, how do you do this with a TCF pair? So like I said earlier, all the server has to do is use F0 and F1 to sample a random Y and entangle his state with the corresponding claw. So the claws here look like mu A R A, where mu A is a single bit. And this is done exactly as I just showed you earlier. He creates a uniform, the server creates a uniform superposition over the domain, applies the function in superposition depending on that bit A. So that bit A tells him whether to apply F0 or F1. He measures the final register to get an image Y. Due to the entanglement in the state, the resulting state will be a superposition over the two pre-images of Y. Now, why is this useful? It's because of what I said earlier. Mu0 XOR mu1 equals S. So once the server entangles his state with the claw, he has taken S and put it into his quantum state. Of course, it's hidden because, okay, so first, so mu0 XOR mu1 equals S. And what that means is I have this equality. So just to break this down, I've rewritten that second register. And so first, let's say when A equals 0, that second register is just mu0, exactly the same as the first line. And when A equals 1, the second register is mu0 XOR S, which is equal to mu1, due to the fact that mu0 XOR mu1 equals S. So all I've done in the second line is rewrite the state entangled with the claw according to the equality that we have about the claw hiding the bit S. And now in this second line, if you compare it to the very first line where I wanted A.S in the second register, it's almost there, but there are two things that are still messing up the state. The first is mu0, but mu0 is just a classical one-time pad. So it's a Pauli X operator. The second thing that is preventing the state from looking like I want it to is this RA. And RA, essentially, it can be turned into a Pauli phase operator. And the intuition is that mu0 is not enough to fully hide S because S is now stored in superposition. So RA is also needed to kind of hide the information about S, which is in the superposition. And RA can be turned into a Pauli phase operator. So what I said here is that these extra parameters serve the purpose of hiding S and can be turned into the Pauli encoding by the server. So essentially all he did was entangle his state with the claw. And the purpose that served was to take the information about S, put it into his quantum state. And the only thing that's hiding it is this Pauli one-time pad. So that was very quick. I'll go through it again, and then I'll ask for questions. Now to recap, what I've said is that the encrypted C0 operation is easy for the quantum server if the encryption of S is a trapdoor claw-free function. In that case, all the server has to do to complete this transformation is to use F0 and F1 to entangle his input state with the claw. And just that procedure, just entangling the input state with the claw, is enough to take information about the bit S, put it in his superposition, and it's only hidden by mu0 and RA, which serve as a Pauli one-time pad. And that's because mu0 is a classical one-time pad, it's just a bit shift, and R0 and R1 can be turned into Pauli Z operators. Now, are there any questions? So I know that was fast, and we can go back if there's any confusion about the previous slide.
So the encryption of S is the pair of claw is essentially description of two functions, right? It's not values. Okay.
It's a public description of two functions. Any more questions?
So this collapsing will be done as part of the homomorphic operation, right? So somehow you just
Yes.
sample these two functions and okay.
Yeah, so this is one step of the homomorphic computation. This encrypted C0 operation is part of the homomorphic computation. And to do the encrypted C0 operation, he uses the TCF pair to entangle his state with the clock.
So there are a few questions also in the Q&A section. Would you like to look?
Oh, yeah, sure. Do you want to?
I can just do it, yeah. So
Yeah,
the first
sorry.
question is, why does the output equal to A times S?
What's the output? Are you talking? Let me go back.
So I think if I understand the question correctly, the question is why this value that you get. So your goal was to actually get an encrypted A times S value, right?
Yeah.
You go from, and the question is why is this value that you actually obtain constitutes an encryption of the value A times S. Why is this an encryption of A times S?
You mean, so why is this final equation? Why is it an encryption of A times S? Is that the question?
That's my understanding of the question. Perhaps, yeah,
Okay, so I think, so it seems like this person understands that this A times S is in the state and you're asking why it's an encryption. And remember, the encryption that we're using is the Pauli one-time pad. So all I need to argue is that this state on the third line is the same as the one on the first line, but it's off by a Pauli one-time pad. And the way to see that is that mu0 is a bit flip. It's a classical one-time pad. So that's the X Pauli one-time pad. And R0 and R1 is a bit trickier, but how it turns out is that if the server performs a Hadamard transform on this R0, R1 register, and he measures, R0 and R1 is converted into a phase. And a phase is just a Pauli one-time pad. So mu0 is an X, a bit shift, and then R0 and R1 are just the phase one-time pad, so a Z one-time pad.
So the R's will somehow collapse to like a bit. So now they're like long strings, and then but somehow after this transformation, you collapse it to this one-time pad bit.
Exactly.
A single bit. Okay.
Yeah, and the one-time pad will kind of be an inner product of R0 and R1 with some other string. And that's achieved by performing the Hadamard transform on it, the quantum Fourier transform.
There's also another question, which is how to generate the encryption. How do you generate encryptions of U0, R0, and R1?
Okay, so that can be done classically with a homomorphic computation, because if the server has access to the encrypted trapdoor of F0 and F1, then what the server can homomorphically compute is he can start with Y, encrypt it, and then using the encrypted trapdoor, he can compute the encryptions of mu0, R0, mu1, R1, and then he's done. And remember, all the server needs to do is output the one-time padded quantum state along with the classically encrypted one-time pad keys. So as long as he can do this computation homomorphically, he's good.
Any other questions?
So are you going to go over like, I mean, the final thing? I mean, I think you started to answer to connect it with FHE like this. I mean, basically the questions that you answered, are you going to go over through it like just as a summary of what you achieved? Right.
Right, okay. So there are different ways to connect it to FHE. I don't know if you're asking about the question that was just asked in terms of computing these keys. Is that what you're asking?
Essentially, because here what you said, it looks like you're saying here is a particular encryption of S, which is not necessarily homomorphic, and here is how it helps you to do the C0, but now you have to connect it one layer above with something which is homomorphic, which I think I understand, but it might be helpful if you have slides to just kind of put everything together.
That's the next part of the talk. So
okay, good.
Yeah,
okay.
Right. So, but just about the question that was last asked, in this picture, the server is outputting the encryption of X and Z. And like I just said, that's possible to compute homomorphically as long as he has the encrypted trapdoor of F0.
Right.
So, okay, any more questions? All right, so now I'm going to continue. But before I continue, let me just say what I've done so far and what remains to be done. So I started off by telling you that the homomorphic computation of quantum circuits boils down to the server's ability to convert a classical ciphertext into a conditional CNOT operation, which is the quantum XOR operation. And I defined something called the encrypted CNOT operation, which formalizes this notion in which the quantum server takes as input a classically encrypted bit S, an arbitrary 2-qubit quantum state, and he conditionally applies the CNOT to the state psi, and he outputs the one-time padded resulting state. And what I just told you is that this conversion is easy for the server if the encryption of S has this special form. If the encryption of S is just a trapdoor claw-free function pair, then the server can very easily perform this transformation just by entangling his state with a random claw. So that's what's been done so far. But now the next step is to link back to classical homomorphic encryption schemes. So if you remember in this picture, the reason that this bit is encrypted is because the server had these parallel classical and quantum computations where he had these homomorphically encrypted one-time pad keys, and he was updating them, and he eventually had to apply a quantum operation dependent on these keys. And because of how this works, because of the fact that the quantum server has to homomorphically update the one-time pad keys, we really need this encryption to be a classical homomorphic encryption, because otherwise the server won't be able to update the one-time pad keys. Like with the encryption that I just showed you with this trapdoor claw-free encryption, I have no idea what the homomorphic properties of that are. So in order to complete this scheme, I really need to link this back. I need to say that if the server receives the encrypted bit S, and this encryption is a classical homomorphic encryption scheme, he can still perform this conversion. And one particularly simple way to do this is, let's say the server receives this encrypted bit S under some classical homomorphic encryption scheme. Is it possible for him to take this encryption and convert it into a TCF pair? So he just sees the encryption of S, and from that, the server should be able to compute public descriptions of F0 and F1, which constitute the TCF encryption of a bit S. And if he can do this, if there are classical homomorphic encryption schemes which kind of allow him to convert encryptions in this way, then he's done, because what he does is he starts with his classical homomorphic encryption scheme, encrypting the bit S, he computes F0 and F1, then he can very easily do the encrypted CNOT operation, and that's all he needs to do. So that's the question. Are there classical homomorphic encryption schemes for which the server can start with the encryption of a bit S and produce this TCF encryption F0 and F1? And this is now just a purely classical question because we know what we need to do. It has nothing to do with the quantum setting anymore. And it turns out that the answer—
Urmila, I think maybe there's some interest in like a bit more, maybe to clarify or repeat what exactly it means to encrypt S, that S is encrypted using a claw-free pair.
Sure.
Can you say again what you mean by this this term?
Let me go back to that. Okay, here's what it means. If a bit is in, okay, this is a TCF encryption of a bit S. It's a pair of claw-free functions, F0 and F1. I've split up the domain, so the first part is a bit. And these properties are just saying that it's a claw-free function pair. The function pairs are injective, they have the same image, there's a trapdoor. It's hard to find a claw, and I've broken up the claw so that mu0 and mu1 are bits. And the final property is what makes it an encryption. And what this says is that for all claws, the first bit of the claw, mu0 and mu1, hide the bit S in the XOR. So mu0 XOR mu1 equals S.
So do you think about this? So it's sort of a one-time encryption, right? So you're giving me the ciphertext, which is F0, F1, and in order to decrypt, well, any way that allows you to find a claw will actually allow you to sort of decrypt this ciphertext.
Yes.
So what is the key generation? Is it a public key encryption or a symmetric key encryption? So there is a encryption scheme. So yeah, just like a syntax. You talked about encryption, but you didn't talk about key generation here.
Right. I didn't talk about key generation.
First of all, is it a public key encryption, or you view it as a public key encryption with a trapdoor, or is it like a symmetric key encryption?
I don't think public key makes sense because, like Zvika said, it's kind of a one-time use thing.
Right. Okay. Yeah, that's true.
Yeah.
So you're saying, do you envision that there is a normal pair of claw-free permutations without the 0-1 distinction, and you're implicitly thinking of constructions that converts a regular claw-free pair G0, G1, takes a bit S and converts G0,
Sorry,
G1 to F0, F1 or something like that?
I'm not following your question at all. Could you repeat it?
Well, it's like your definition is like there is, usually there should be some distribution of S. So you're saying there is a procedure, right? I mean, it's just an incomplete. You told about encryption. You didn't talk. I think that's a confusing. So do you think that there is a normal claw-free permutation pair, and you skip the part how from normal claw-free G0, G1 you generate F0 and F1, or F0, or there is no G0, G1, you already define F0 and F1, but then you didn't tell about, what is the role of bit S? Are you saying given a bit S, you can sample F0, F1 with this property? There is like a syntax part missing here, like a connection.
Well, I mean, so Trapdoor claw-free function pairs can always be sampled from some set. So sure, you could say that it's a symmetric encryption scheme where he just samples the key of a Trapdoor claw-free function.
So given S, so you're saying given S, you're saying there is a generation algorithm that takes a bit S and samples a pair F0 and F1 having this property, right? Having these three properties that you stated.
Sure. Yeah, you could do that.
In particular, the semantic security is part of the definition. It's not something that follows like from the claw-freeness.
Right, it does not follow from the claw-freeness.
Okay, so essentially you have, I see.
It could be that he can find a claw, that he can find mu0 and mu1, but he can't find a claw, and then he'd break the encryption. So it does not follow from claw-freeness.
So claw-freeness is necessary. I mean, clearly, if it's not claw-free, you break the encryption, but the semantic security is part of your definition of TCR.
Yes, claw-freeness is necessary, but not sufficient. And the reason that this isn't fully defined is because this is kind of like a stepping stone. It's not. So what I'll show next is I'll just link classical homomorphic encryption schemes. And this is never kind of used on a standalone.
Got it.
Yeah.
But Urmila, actually, doesn't the semantic security follow from these properties? Because if I know S, if I can recover S somehow, then I can just find a claw by getting some arbitrary mu0 and then setting mu1 to be mu0 XOR S. And then I found a claw and broke the claw freeness, right?
You didn't find a claw because you didn't find R0 and R1.
How do you find
out? Sorry, right. You need to find also the R's.
So that's why it's not obvious.
Oh, S is a bit even. Yeah, sure.
Yes.
Also, but my understanding, maybe I'm wrong, it looks like for S equals 0, there is one pair of function of 0 and a 1. For S equals 1, there is a completely different pair of functions. So that was my confusion. It's not like there is like one fixed F0 and a 1, because once you fix F0 and a 1, it kind of fixes S.
Yes.
So somehow it seems like that, I was also curious about this kind of reduction, but it looks like it is part of the definition, the semantic security.
Yeah. Okay, so I'll continue now to linking this to classical homomorphic encryption schemes. So the question here was whether there exist classical homomorphic encryption schemes for which the server can take as input the encryption of a bit S under that scheme and convert it to a TCF encryption. So he can take as input the encryption of a bit S and produce public descriptions of the functions F0 and F1 for which each claw hides the bit S. And it turns out that there are classical homomorphic encryption schemes for which this conversion is possible. And that's what I'm going to show you next. So what I'll do now is I will start with the encryption of S, define the pair of functions F0 and F1. And then I'll say that if the classical homomorphic encryption schemes satisfy certain requirements, then F0 and F1 actually constitute a TCF pair encryption. And the next step I can do is take all these requirements and put them together. And once we formalize these requirements, we can say that if a classical homomorphic encryption scheme satisfies these requirements, then the server can use these schemes to convert to TCF encryptions and then apply the encrypted C0 operation. And therefore, the server can use these classical homomorphic encryption schemes to homomorphically evaluate quantum circuits. And I call classical homomorphic encryption schemes which satisfy those requirements quantum capable schemes. And those are just classical homomorphic encryption schemes which can be used to homomorphically evaluate quantum circuits. And the final thing that I'll tell you after I'm done with all of this is I'll tell you that there does exist a quantum capable classical homomorphic encryption scheme, and this scheme can be constructed by combining existing schemes in literature. So now I'll start by defining F0 and F1, starting with the encryption of a bit S. And this is just a reminder of what I want the TCF encryption to look like. And I'll need this reminder because what I'm going to do now is define F0 and F1, and then tell you what the classical homomorphic encryption scheme has to look like in order to satisfy these requirements. So F0 is easy to define. It's just the encryption function. So we're working with a public key classical homomorphic encryption scheme. So there is an encryption function which takes as input a bit to be encrypted and some randomness. So mu0 will be the bit to be encrypted, R0 will be the randomness, and F0 will just take as input both and output a ciphertext. Now F1 is almost the same as F0, but it's shifted by the homomorphic XOR of the ciphertext encryption of S. So this is where we use the encryption of S to define F0 and F1. Now, so F1, it takes as input mu1 and R1. It first applies F0, so it computes the ciphertext of the bit mu1 with randomness R1. Then it homomorphically XORs the encryption of S to that ciphertext to get the output of F1. So now I've defined these two functions, F0 and F1, starting from the encryption of S. And these functions can be publicly evaluated just given the encryption of S. And now the next thing I need to do is I need to tell you that these two functions, F0 and F1, actually constitute a trapdoor claw-free function pair, or a trapdoor claw-free encryption of the bit S. And before that, are there any questions about the definition of this function, of these function pairs?
I have a question. So do you still require an encryption of the trapdoor starting with an encryption of this bit S along with this TCF pair F0, F1?
Which trapdoor? So I will.
So the trapdoor for this claw-free pair?
Well, I haven't defined that yet. So I'm starting with an encryption of a bit S, and then I'm going to create a TCF pair. And that TCF pair will have a trapdoor, and the quantum server will have to have access to the encryption of that trapdoor in order to do this key update.
Yeah.
If that's what you're asking.
Yeah. So you still need this property, right? You need the quantum server to have an encryption of the trapdoor.
Yes, I will always need that property for the key update.
Okay.
Yeah.
So this is you're defining a particular construction of TCF pair from a homomorphic encryption. And I guess you will later tell us what properties of homomorphic encryptions you need, but this is a construction of TCF pair from some kind of special kind of homomorphic encryption. Is it correct?
So far, there's nothing special about the homomorphic encryption scheme. I started with an arbitrary classical homomorphic encryption scheme encrypting a bit S. And I'm saying from that, I can define these functions F0 and F1. But now what I need to do is say that actually F0 and F1 constitute a TCF encryption.
Good.
And to say that, the classical homomorphic encryption scheme will have to satisfy certain properties.
Good. And just an aside, I mean, obviously this is what you need for this construction, but just as an aside question, if you forget about FHE properties, I mean, this is like a clean classical definition, TCF encryption. Can you build it out of curiosity? I don't know if it's interesting. Can you build it from any normal claw-free permutations? I mean, what, you know, like if you just concentrate on the standard properties, can we build it from factoring, from any claw-free permutation? What do we know?
I don't know, and I don't know if anyone has studied this.
Okay.
So I don't know if anyone else knows. Maybe even no other speaker. Okay.
All right.
Yeah. Okay. So I've defined these functions, and now I need to tell you that these functions are a TCF encryption. And to do that, let's just go through the properties. So let's start at the last property. We need all claws to hide the bit S. Now, this is very easily satisfied because of how I've defined the functions. So F1 is just a shift of F0 by the homomorphic XOR of the encryption of the bit S. So just by this definition, it follows that if F0 and F1 map to the same point, then mu0 XOR mu1 equals S. That follows from the definition. Now, this also implies the claw-free property because if it were possible to find a claw using this public description of the functions, then the server could just break the initial encryption of the bit S. So those two properties are straightforward. The next one is the trapdoor property, and this is the first time I'm going to have to put a constraint on the classical homomorphic encryption scheme. And what I will need is that the classical homomorphic encryption scheme must have a trapdoor which allows for randomness recovery from ciphertext. Because eventually what we want is that when we look at an image Y, we're able to recover the pre-image, which is mu0, R0, or mu1, R1. And so looking at a ciphertext Y, we have to be able to recover the randomness which was used to create the ciphertext. And this is a condition on classical homomorphic encryption schemes because there are schemes for which this requirement does not hold. So this is the first constraint. The classical homomorphic encryption scheme must have a trapdoor which allows for randomness recovery. And this requirement also implies that F0 and F1 are injected. The final constraint, which is the hardest to satisfy, is that the function pairs F0 and F1 have to have the same image. Now, this is tricky because given how I define the functions, the images won't overlap perfectly because F1 is F0 shifted by the homomorphic XOR. So this is hard to satisfy, and what I'm going to do is I'm going to weaken this condition of having the images overlap perfectly, and I'll weaken it just so that it's sufficient for what I need in my setting. So the weaken requirement says that instead of the images overlapping perfectly, there exists a distribution over the domain of F0 and F1, such that the resulting distributions over the images are statistically close. An equivalent way of stating this is that there exists a distribution over ciphertext which doesn't change much if it is shifted by the homomorphic XOR of the encryption of this bit S. And just to tell you why this is what I need in my setting, remember why we need the same image requirement. We need the fact that when the quantum computer applies this function in superposition and he measures the image, then the remaining state will collapse to these two pre-images, to this claw. Another way of doing that with a quantum machine is he doesn't have to create a uniform superposition over the domain. He can create a superposition according to some distribution and then measure Y. And as long as for that distribution, the image Y still has two pre-images, then we're okay. So that's what this requirement is formalizing. It's saying we don't need the same images. We just need a distribution for which the resulting distribution over images is statistically close. So this is it's a weaker requirement. It's enough for quantum homomorphic encryption. And now what I need to tell you is what a classical homomorphic encryption scheme has to look like in order to satisfy this weakened requirement. And before that, are there any questions just on this requirement or on any of the requirements I've listed so far? Okay, so now I need to tell you what a classical homomorphic encryption scheme needs to look like in order for this requirement to hold. And I'm going to start with a very simplistic picture of what encryption schemes might look like. So let's imagine that the encryption of a bit 0 is just a random element sampled from some subgroup H, perturbed by some small amount of noise epsilon. So that's the encryption of a 0. And the encryption of 1 is almost the same, except instead of sampling from H, you would sample from some coset of H. So this is just a very simple form of what encryptions look like. And I'm using this form because I want to try to describe to you what a classical homomorphic encryption scheme could look like in order to satisfy this requirement. So let's say the first thing that I want from this scheme is that throughout the computation, the ciphertext form has this nice form, like encryptions of 0 are sampled from the subgroup and perturbed by some amount of noise. Encryptions of 1 are similar. And as you compute on the ciphertext, this form doesn't change. The noise might change and grow in different ways, but the rough form of just having something from this subgroup H perturbed by noise remains the same. So this is something that I'll call the ciphertext form requirement. And the next thing that I would like is that the homomorphic XOR operation is natural in the sense that the homomorphic XOR is just adding ciphertext. Now, if these two requirements hold, then it's quite easy to construct distributions which satisfy this requirement. And to see that, let's assume that the noise of this ciphertext, the encryption of S, is epsilon. Then all we need to do is choose an initial distribution over noise, let's say some Gaussian distribution over noise, where the width of the Gaussian is sufficiently larger than epsilon. Now, if that holds, so we look at our initial distribution over ciphertext, if we take this distribution and shift it by the encryption of S, it will barely change because the width of it was large enough to essentially erase the noise of S, which is epsilon. And this technique is well known to cryptographers, and it's called noise flooding, and it's used in circuit privacy. And that's exactly what I'm using here. So I'm just using these properties to say that the distribution is easy to define because we can just define a distribution which doesn't change much when it is shifted by the encryption of S. So what I've done here is I've weakened the distribution requirement. I've weakened the same image requirement to say that all we need are distributions which are statistically close. Then I said that this requirement is easy to satisfy if the homomorphic encryption scheme has some nice properties. So if the ciphertext form remains roughly the same throughout the computation, and if the XOR operation is just addition of ciphertext, then these things are easy to satisfy. And now the next thing I need to tell you is, are these easy to satisfy? Are there classical homomorphic encryption schemes which satisfy these requirements? And before that, are there any questions on just this slide or what this requirement means? So my next problem is that I needed these two requirements. I needed the ciphertext form to stay roughly the same throughout the computation, and I needed the XOR, the homomorphic XOR, to just be the addition of ciphertext. And from what I know, known schemes don't satisfy both of these requirements at the same time. So I did have to change one thing slightly. And what I changed was that I used two schemes, one which satisfied the form requirement and one which satisfied the XOR requirement. And what I did was that the quantum server can use a scheme which satisfies the form requirement throughout his classical homomorphic computation. But whenever he needs to do an encrypted CNOT operation, whenever he needs to take one of his ciphertexts and convert them to a quantum operation, then he can take his homomorphic ciphertext, convert it into an alternate scheme which satisfies only the XOR requirement, and then use this converted ciphertext to run the encrypted CNOT operation. And so now, so far, I've told you all of the requirements that I need from the classical homomorphic encryption scheme in order to allow this conversion from a ciphertext to a TCF pair. And these requirements can be pretty easily formalized to define something called quantum-capable classical homomorphic encryption schemes. These are homomorphic encryption schemes for which the server can start with the encryption of a bit S, convert it to a TCF encryption, and then use that TCF encryption to apply the encrypted CNOT operation. And so these schemes allow for homomorphic evaluation of quantum circuits. And the final thing that I need to do is tell you that there does exist a quantum-capable classical homomorphic encryption scheme, which I can construct by combining existing schemes in literature. And I'll tell you that briefly, and it'll be technical, but hopefully it'll just be for the experts to follow. And if you don't follow, don't worry about it. But before that, are there any questions so far?
Yeah, so there's a question from the audience on, so the question is, why doesn't any FHE with circuit privacy sufficient for what you need?
Because circuit privacy doesn't necessarily imply this distribution requirement. So I am using one circuit privacy technique to satisfy this, but to me, it's not clear that circuit privacy, if you just take the definition, would imply that you'd get these overlapping distributions.
Is it a requirement on the distributions or on generating onto these distributions?
Yeah, so the requirement is that you have a distribution for which the images are statistically close. And on top of that, you have to be able to create a superposition over the distribution. So you're right that is actually the constraint, because from what I know, there are some circuit privacy techniques which are kind of hard to undo. So it would be hard to create a distribution, create a superposition over those.
So is the person who asked the question is satisfied?
So noise flooding is one way to get circuit privacy, right? I mean, there are there are a few other ways to do it, some even nice and algebraic actually. And the reason these guys don't work is because either they work, or if they don't work, it's because of the superposition requirement. Yes.
Yes, and Zvika would know more about that because in his paper,
You do this thing, Zvika.
Yeah.
This G inverse multiply by G inverse type.
Yeah, you need to be careful about sort of generating the right superposition.
Okay, I got it. Got it.
Okay, any more questions on the requirements so far? Okay, and now just to finish up, for those of you who are very familiar with existing classical homomorphic encryption schemes, I just wanted to tell you what schemes I'll be using. And just to remind you, I need a scheme for which the ciphertext form stays roughly the same the whole time, meaning the main structure is the same, but maybe the noise is changing. And then I also need a scheme for which it is easy to convert from the original scheme, and the XOR operation is natural. So let me just tell you briefly what these schemes are. So the scheme that I'll use for the ciphertext form requirement is the Gentry-Sahai water scheme from 2013. And just to remind you, this scheme uses standard LWE encryption. So it uses a regev encryption, but it takes these vector ciphertexts and expands them into matrices. And the nice thing is that these ciphertexts stay roughly the same throughout the computation, only the noise changes. But remember that I need randomness recovery for the trapdoor. And the GSW scheme does not have randomness recovery because the regev scheme doesn't have randomness recovery. Luckily, there's an easy solution to this. Instead of using regev, use the dual of regev, which is the Gentry-Piekert-Vikundanathan scheme. And so what I can do is use the same structure of GSW13, which is expanding these vector ciphertexts into matrices, but instead of using the regev ciphertext, I'll use the GPV ciphertext. And now we have a scheme which satisfies the ciphertext form requirement and has randomness recovery. It has a trapdoor for randomness. Now the final thing I need is I need a scheme. Oh, so the problem with this is that the XOR operation isn't natural. The natural operation for this scheme is the NAND gate. To build the XOR gate, I'd have to use the NAND gate. So the XOR operation wouldn't just be adding ciphertext. So to take care of that issue, what we can do is whenever the server needs to apply the encrypted CNOT operation, so he needs to do this XOR, he just takes his GSW ciphertext and he converts it back to a GPV ciphertext. And to do that, all he has to do is pick one column of his GSW ciphertext. Now that resulting ciphertext has a very nice XOR operation because in the GPV scheme, the XOR operation is just addition of ciphertext. So this is all. I just wanted to briefly say what schemes I use and how I use them. So all I'm doing is I'm combining the GSW scheme and the GPV scheme to get all the requirements that I need. Now let me just wrap up the talk. So I started by telling you that quantum homomorphic encryption boils down to the ability of the server to convert a classically encrypted bit into a quantum operation. And I called this the encrypted CNOT operation. Then I told you that this encrypted CNOT operation is quite easy for a special type of encryption, which I called a trapdoor claw-free encryption. In this encryption, the encryption of a bit S is just a trapdoor claw-free function pair for which each claw hides the bit S. And given this type of encryption, all the server needs to do to perform this encrypted CNOT operation is entangle his state with the claw. Then I needed to link this back to classical homomorphic encryption schemes. I needed to say that there are classical homomorphic encryption schemes for which the server can start with the encryption of a bit S and convert it to a TCF pair, which hides the bit S. And it turns out that there are requirements which we can state for a classical homomorphic encryption scheme for which, if these requirements hold, then the classical homomorphic encryption scheme allows this conversion to a TCF pair. I called such schemes quantum capable, and these schemes allow homomorphic evaluation of quantum circuits. Finally, I said that there are existing schemes in literature which can be combined to form a quantum capable scheme, and all these schemes depend on the security of learning with errors in the presence of quantum computers. So what this is saying is that a quantum capable classical homomorphic encryption scheme can be constructed under the computational assumption of learning with errors. And if we put all that together, what it's saying is that blind delegation of quantum computations by a classical client is possible under the assumption that learning with errors is quantum secure. That's all I have for my talk. Thanks for listening.
Thank you. Any more questions?
There were a lot of questions during the talk.
Yeah, certainly.
I guess I have one sort of parting question, which is, why do you need GSW here? It wasn't completely clear to me why, why GSW?
This could have been a misunderstanding on my part. I think we've talked about this before. I thought I needed it because I thought in the other schemes, the ciphertexts get messier as you continue with the homomorphic computation. And I thought that for GSW, the ciphertexts stay the same. So it could be that my understanding of the other schemes was not good enough, and that actually those ciphertexts have a nice form throughout the computation and you can use them.
So they do have a nice form through the computation. It's just that, so when, you could think about homomorphic evaluation as sort of two steps. One makes the ciphertext messier, but then you quickly bring it back to a nice form, and then you keep continuing that sort of
yeah.
thing. So yeah, maybe we can take it offline.
Yeah, I think you brought this up earlier, and
yeah.
I think we agreed that it sounded good. I don't know. Yeah. I think Zvika might know more about this, but I'm.
Zvika, why doesn't BB work?
And I don't think that the reason that GSW is used is because that's the only solution that works. It's just because this is a solution that works, and GSW is sort of the canonical scheme that you try in this situation. I think in Urmila's paper, there's actually just a list of requirements, right? So yeah. You can just try to sort of go over them and see if other schemes are going to have this. And I don't see why not. So I don't see like
I thought I did, and I didn't see.
You do need the randomness recovery. That's important.
Sure, absolutely. But randomness recovery with the Trapdoor is usually okay.
Yeah, because you can always just convert to the dual, right?
Yeah, for example, yeah, that's right. But anyway, I'll take this off. We'll take this offline.
Yeah. Just a clarification question. How many this encryption of S that the client actually need to send to the server? Is it as big as the circuit or not?
Oh, it depends. It's the same as classical. So if you assume leveled, if you want leveled fully homomorphic encryption, then it's going to correspond to the depth of the quantum circuit. And if you want, if you're willing to assume circular security, then it has nothing to do with the size.
I see. And everything you said, you focus on the fact that there is a classical client. If the client is also quantum, so everything still works, right? The client, yes. If I want to do like quantum input and output.
Yes, it's all exactly the same.
Okay, thanks.
Yeah, no problem.
So I have another question. This is probably a quantum dummy question, but you said at the beginning of the talk that the output of the C0 on an encryption of S should be encrypted because otherwise the server would violate CPA security of S. But this is only if the server performs a measurement, or is there some imaginable way that is there some way one could imagine the server not being allowed to measure and also not end up with an encryption of S?
Encryption of S? Sorry, I thought you didn't mean the encryption of S, but you were talking about the encryptions of Z and S. So no, it's not, because what I need the encrypted C0 operation to hold for an arbitrary 2-qubit quantum state. And if the output is not encrypted, then it can't hold for an arbitrary 2-qubit quantum state because the server. Yes, exactly. And that has nothing to do with measuring or not, because what he could do is he could set his state so it's a standard basis state. It's not even in superposition. And so he doesn't even have to So I don't think there's any way that you could do it if it's not encrypted. You would just violate security.
Okay, thank you.
Yeah.
Another question from the Q&A panel. So the question is why you need to why the randomness of the encryption is actually the input to the claw-free function and not some other, why is there this connection between the randomness of the encryption and the input of the claw-free function, and you don't use some other value as the input for the claw-free function?
What other value could I use? I just picked the most natural.
So maybe is there a reason to sort of think that this would be the natural thing to use, the randomness of the encryption?
To me, it seemed natural because I was just defining F0 and F1 to be the encryption functions. And your public encryption function, it takes as input a bit and some randomness. There could be many other ways of doing this. I'm not saying that other ways are bad. To me, it was just the first thing that came to mind.
Any other questions? All right, let's thank Urmila again. Thank you very much.
Thanks.